again, this is our second video now, looking at the basics of electronic circuits and systems. In the last video, we talked about the difference between series and parallel circuits and how voltage and current behaved in those. And we also touched on the idea of charge a little bit. Now we're going to look at that in a bit more detail. We need to be able to calculate the voltage and the current and resistance and charge in circuits. Okay, and this being physics, of course, is going to involve equations. So the first one we will look at is the link between voltage, current, and resistance. These three variables, these can all be linked with one formula. Okay, this is probably the most important formula we'll do in electronics at that 5 level as well. And we call it Ohm's law, okay, named after the guy who discovered resistance. So that formula is V equals I times R. And in this formula, V is your voltage measured in volts, I is your current measured in amps, and R is your resistance measured in ohms. Now, if we have a little minute to think about this equation, where it comes from, it actually does make sense. So what this equation is telling us is that your voltage here, this will get bigger if your current is bigger or if your resistance is bigger. That makes sense. Remember, your current is the electrons being pushed around the circuit. So if there is a bigger current, your electrons are being pushed more, there has to have been a bigger voltage to push them. Okay? If your resistance is bigger, remember your resistance is pushing back against the current. If your resistance is bigger, your voltage needs to be bigger to overcome that, to push against the resistance. If we think about it another way, in most situations your voltage stays the same. Your voltage is constant because it's coming from the mains power supply or a battery or something. So if this here, your voltage, has to stay the same, what's going to happen if your resistance gets bigger? So your current then here is going to get smaller, and again that makes sense because your resistance is pushing against that current. So if your resistance is getting stronger and stronger and stronger, it can push back against the current more and more. That will make the current smaller. Now, obviously, if your equation is just your question is just asking you to work out voltage, that's nice and easy. You times it by your current, times by your resistance, sorted. And this equation here is given to you in your data booklet. But there might be a situation where we know the voltage, and so we want to work out the current and resistance. So here we'll do what we always do in physics and sometimes in maths. We'll use a little triangle to help us rearrange the equation and remember how that is done. So we split our triangle into 3 sections. In the top section, we're going to put V for voltage. And then in the bottom 2 sections, we're going to put I for current and R for resistance. Now, remember, the way these triangles work is we cover up the letter we're wanting to find out, and that tells us what our equation is. So I'm going to use a little laser pointer here to cover them up because I've not got no other way of doing it at the moment. But so if I cover up the V here, that leaves me with I next to R, so I times R, like I have in my equation, V equals IR. Now say I want to work out the current, I'm going to cover up I. That leaves me with V over R, which is voltage divided by resistance. And then if I want to work out resistance, I cover up my R. That leaves me with voltage divided by current. Now, let's have a look at this, okay? It's a bit easier to understand when you actually see it used with numbers and in the context of a question. So we'll look at a couple of examples of this. And our first one is a nice simple one. A lamp in a circuit has a resistance of 0.5 ohms. If the current passing through it is 2 amps, what is the voltage across the lamp? So remember, the first thing we do when we have a question in physics is we write down the variables. We write down what we know and we write down what we're being asked to find out. So if we do that here, we'll write down that we don't know the voltage. We're being asked to find that out. We know the current is 2 amps and we know the resistance is 0.5 ohms. Another reason we write these down is because you might not always know the equation you need to use. Here, you know you're going to be using V equals IR because that's what we're practicing. If you saw this question in a test or an exam, you wouldn't necessarily know what equation to use. But if you write down all the values you have, you can see that and say, oh, I've got a voltage, I've got a current, I've got a resistance, I just need to look through my equation sheet and find an equation that has these three things in it. Okay, and when you do that, you'll get this equation, V equals IR. And then we just substitute in our numbers. Okay, so that gives us voltage equals 2 times 0.5. So voltage equals 1 volt. Okay, it's a very weak circuit apparently. Remember, your units there are just as important as the number. Okay, right, let's look at a slightly trickier example then. So our second example. A battery supplies 12 volts to a motor. What is the resistance of the motor if there is a current of 0.2 amps flowing through it? This is sort of a situation I was talking about before, where we know the voltage is a constant steady voltage coming from a power supply. So once again, we're going to write down what we have and what we're trying to find out. So we have the voltage, that's 12 volts. We have the current, that's 0.2 amps. We don't know the resistance. That's what we're being asked to find out. But we know we've got VI and R, so it's going to be some form of this equation we're going to use. But we'll use our triangle to rearrange it. Now, excuse me for a second while I try and draw a triangle, probably very badly on the PowerPoint. But here we go. Here's our triangle. And we'll put V at the top, I and R, and we'll just separate them to make it super clear. Not too bad. Okay, so we're trying to find out resistance. That means we're going to cover up the R. Okay, that leaves us with voltage on top of current. So that leaves us with resistance equals voltage over current, which is voltage divided by current. And again, just put in the numbers we have. So resistance then equals 12 divided by 0.2. Resistance equals 60 ohms. Again, units are important. Remember, resistance is the tricky one, where the units we use this omega symbol here. Now, this is about as tricky as Ohm's law could get at this level. Okay, we could be asked to work out the current instead, and then we'll just rearrange it like we did there, and this time we'd have current is voltage over resistance. Okay, but that's sort of the core ways you could use that equation. What we're going to look at now is a second equation. Now, this one you don't use so much at this level, but most of you are going on to do Nat 5 and it will come up a lot there. So it's good to get the practice in for it now. And that one involves the other main property we talked about with circuits. Okay, so this links charge, current and time. Now, if we remember, charge is what's actually flowing around the circuit. So remember, your current is this charge moving around the circuit. That charge comes from the fact that all electrons have a negative charge. And so these three things can be linked by an equation again, just like the others could be. And the equation that links these is Q equals IT, where Q equals your charge, and that's measured in coulombs. I is your current, which is measured in amps, and T is your time, which is measured in seconds. Okay, this one we don't need to remember the name of it, okay, so this one doesn't have a fancy name like Ohm's law does. We just need to know this equation, but once again, we will need to be able to rearrange it. So if we look at our triangle here, we'll split it up into 3 again, and we'll put Q at the top, and we'll put I and T next to each other. And just like before, if you cover up the thing you're after, it tells you the equation. So if we're trying to find out time, we cover up T. That tells us we'll have a charge divided by current. Now again, we've just got a couple of examples of this, so you can actually see the equation in action. Hopefully that makes it make a wee bit more sense in your heads. So our first example of this equation then. We've got a current of 3 amps flowing through a kettle for 2 minutes. What is the charge of the kettle? So once again, standard approach for the start of a physics question. Write down what we know. We don't know the charge, that's what we're trying to find out. We do know the current and we do know the time. However, there's a little bit more work we need to do now. The standard units for time in physics are not minutes, they are seconds. So if you're doing a question that has time in it, that time must always be in seconds. So we need to change this 2 minutes here into seconds. So each minute is 60 seconds, so 2 minutes is 2 times 60 seconds equals 120 seconds. And it is this we use in the equation, the 120 seconds. That's something to look out for and something people trip up on. Remember, your time has to be in seconds. So we've got Qi and T. That tells us we're using this equation. We don't need to rearrange it because it's Q we're trying to find out. So we'll substitute them in. We'll put 3 in for the current. We'll put 120 in for the time. So our charge there of the kettle is 360 coulombs. Again, nice and simple, no rearranging of the equation needed, just need to keep a check that everything is in the correct units. So let's look at a slightly trickier example question. How long would you need to leave a 1.5 amp heater on for to create a charge of 135 coulombs? Let's write down what we have. We know the charge straight off, that's 135. We know the current is 1.5. We don't know the time because remember the question said how long, so it's asking us for a time. We know it's going to be some form of this equation because that's the 3 things we were told or we were looking for. But again, we'll need our little triangle, which I will try not to draw a terrible one of. Got our triangle, we've got Q at the top, I, this is pretty tricky with a mouse, and then T. We'll just split them up again to make it very, very clear. We're trying to work out time, so we'll cover up time with a laser pointer again. So that's going to tell us that time is equal to Q over I, T is equal to Q over I, and we substitute in our numbers. So T is equal to 135 over 1.5, put that in the calculator, and we get that T is equal to 90 seconds. Now, notice here, we don't say 1 minute and 30 seconds, we don't say 1.5 or 1.5 minutes, we leave the answer in seconds, okay? So the time it would take for that heater to create that much charge is 90 seconds. Okay, hopefully that was clear going through those 2 equations and the examples. As usual, if you have any questions about that, feel free to get in touch with me. And if you could, once you have watched this video, go back through to the PowerPoint, which I'll make available again, and make sure you take notes of everything that appears in the blue boxes. Okay, thank you again, and goodbye.